To begin the chapter on nutrient cycling, we'll start with understanding how nutrients cycle within lakes. Active absorption of nitrogen and phosphorus by phytoplankton often maintains extremely low nutrient concentrations in surface waters of unpolluted lakes. This statement represents some of the important factors to think about for lakes. We're going to think about nitrogen and phosphorus, we're going to think about the role of phytoplankton, and the concentrations of nutrients in the different waters. In addition, we need to think about surface waters versus deep waters, and unpolluted versus polluted lakes, meaning those lakes that have high nutrient inputs versus those lakes that have low nutrient inputs. The first thing to understand about nutrient cycling in lakes is that thermal stratification isolates surface waters. So in a typical lake, in your surface waters, most of the nutrient cycling happens here, and any nutrients that make it down into the sediments or to the lower portions of the lake might not necessarily be able to cycle back up into the surface waters where most of the production happens. This figure shows thermal stratification in Lake Erie. On the x-axis, we have distance from the western to the eastern basis in kilometers. So we've got over 100 kilometers of distance here. And this is depth in meters. So here's the surface, 5, 10, 20 meters below the surface. And then here are the temperatures. So this was taken, these thermal profiles happened in August. And you can see that the surface waters are relatively warm. As you go down, temperatures get colder. Most of the mixing occurs here, where the waters are relatively warm and uniform in temperature. As you go downwards, the density of that water increases, and there's a lot less mixing between the bottom waters and the top waters because of the thermal differences and the density differences that they represent. So there's almost like there's two nutrient cycles within the system. One in the surface waters that happens here, and then there might be transfer to lower waters, and there might be cycling that occurs down at the bottom. And these two cycles would be relatively disconnected, as long as that thermal gradient is present. So when we think about lakes, nutrient cycle in the top waters, and grazing is really important in the cycling of those nutrients. And we've talked a little bit about that before. But nutrients also get buried. So there's movement of nutrients through the vertical profile in waters, and those nutrients often get buried in the sediments. When we think about lakes as part of the land surface area, on a global scale, it's about 3% of the land surface area that's covered by lakes. Some of these lakes are relatively large. Here are the Great Lakes. Lake Superior is the largest among those, but actually there's a lot of relatively small lakes. Lake Mille Lacs here, northern Wisconsin there, that still represent a relatively large area, but there's differences in the way that nutrients cycle in a large lake versus a small lake. So we have to think about differences in shallow versus deep lakes. Now it's somewhere on the order of 40% of all the lake surface area is less than a kilometer squared. So almost half of the lakes in the world are actually pretty small. The rest tend to be larger lakes. So understanding small shallow lakes versus large or potentially deep lakes are almost equally important on a global scale. One of the differences between shallow and deep lakes is that deep lakes, when they're really deep, don't actually mix seasonally. So most of that cycling happens in the top waters, and there's no exchange of waters from deep to shallow in the very deep lakes. As a consequence, the hypolimnion is often anoxic. So if there's no mixing, there's no way that oxygen-rich waters can get down into the deeper areas. Decomposition is still going to proceed in these deeper waters, and that's going to use up oxygen, and these typically tend to be anoxic. In addition, when we take a look at differences among lakes, they're going to differ in their stoichiometry. They're going to vary in the ratios by which nitrogen and phosphorus are supplied and cycle within them. This is figure 9.2, which shows the relationships between average summer total nitrogen and phosphorus concentrations in surface waters of the world's lakes. So each one of these points is a different lake. On the x-axis, we have total phosphorus in micrograms per liter, and this has been log transformed. So to go from 1 to 2 is a 10-fold increase, from 2 to 3, another 10-fold increase in the concentrations of phosphorus in the surface waters during the summer. Here's total nitrogen on the y-axis, again 2 to 3. It's log transformed, means a 10-fold increase, 3 to 4, a 10-fold increase in nitrogen concentrations. In general, there's a constant ratio across all of the lakes. Those systems that have low phosphorus concentrations have low nitrogen concentrations, and vice versa. But there's also an axis orthogonal to that, more or less, that shows differences in the ratios of phosphorus concentrations to nitrogen concentrations. So there are some systems that at a constant nitrogen concentration have a lot more phosphorus available than other lakes. So this lake has a relatively low phosphorus concentration relative to how much nitrogen, and this one has a relatively high phosphorus concentration relative to the nitrogen concentration. If we looked across the different lakes, these lakes are separated out by the sources of nutrients to them. So those systems that have a relatively low P concentration, so a low N to P, those systems tend to get runoff from unfertilized fields. As you work across this gradient, you're going towards more and more impact from humans. So by the time you have raw sewage that's being introduced into the lakes, the phosphorus concentration goes up a lot more than the nitrogen concentrations. So the impact of humans into the system, really increasing nutrient availability, is not only potentially to change the total nutrient concentrations that you find of nitrogen and phosphorus, but the amount of phosphorus that you find relative to the amount of nitrogen. And by the time you're here, I didn't do that right. By the time you're here, your N to P ratios are relatively low because you have a lot of phosphorus and not a lot of nitrogen. And that's one of the consequences of having a manure or sewage that's going to get into the waterways. Now, in addition to thinking about the concentrations, we need to think about the residence times in order to understand the cycling of nutrients within lakes. This is figure 9.3, and it shows the relationships between water residence time and phosphorus input to different temperate lakes. To understand this graph, let's look along the x-axis. This is water residence time. 10 to the 0, 10 to the first, that's a 10-fold increase. 10 to the 0 means that you have 1 year, 10 to the first, 10 years, 100, 1,000, and then somewhere right around here is probably 1 month. So there are lakes that have water that on average stays within that lake a year. Other lakes that water resides in the lake for 10 years, 100 years, even up to almost 1,000 years. On the other end of the spectrum, there are some lakes that the water stays in them for only on the order of a month. This can be due to two different factors. For example, the size of the basin and the size of the inputs. So if you increase the size of the inputs but hold the basin the same, that mean residence time is going to go down. Alternatively, if you have a certain input and you compare a large lake or a smaller lake, changing the basin size, if the lake becomes smaller for the same amount of input, also decreases your residence time. So think about these lakes as having a lot of input and or a pretty small basin. On the y-axis, we have phosphorus input, megagrams per meter squared per year. And this would be milligrams per meter squared per year, where the area is going to be per meter squared of lake. Again, log axis, 10 to the first, 10 to the second, 10 to the third. And across lakes, you generally have a negative relationship. This is not a causal relationship. The mean residence time is not determining what the phosphorus input is, but what that means is that those lakes that tend to be relatively large, that have a long residence time, tend to be in areas where the phosphorus input per unit area of lake is relatively low. On the other hand, by the time you get to these smaller lakes, the phosphorus input is going to be a lot higher. And part of that is just going to be based on circumference also, for example. But what's instructive here is to think about variation in phosphorus input for a given water residence time. So if we take 1 year, lakes that have residence times of about a year, there is 100-fold difference in the phosphorus input across those lakes. So these lakes down here will have a lot less phosphorus being put into them than these lakes up here. These lakes are going to eutrofy and be a lot more productive than these lakes here. If we go along the other axis, like this, what's happening is we're holding phosphorus input constant, but we're changing residence time by 100-fold. In this case, you'll have a constant phosphorus input, but it's going to flush out a lot faster on this side than here. And that's going to allow phosphorus to accumulate in that lake, in the lake with the longer residence times than those lakes that have a short residence time. So the impact of a given amount of input is going to be a lot higher the longer the residence time.